Hi guys! In this video, I will work through the Borde-Guth-Vilenkin theorem. This theorem shows that an expanding universe must have a beginning. By universe, I mean all the particles we are composed of, observe, and interact with. To put it more precisely, the time experienced by a particle in an expanding space must be finite and not past eternal. This remarkable result can be derived using relativity. This may seem obvious since the Big Bang is considered to be the beginning of the universe. However, it is conceivable that there was an eternity prior to the Big Bang. This theorem shows that for a universe with spatial expansion, time had a beginning for all particles, perhaps at the Big Bang. In 3D Euclidean space, the coordinates of a particle can be represented by three numbers. These are typically written together as a vector. Changes in coordinates, or motion, can also be written as a vector. These changes can be summed in quadrature to give you the magnitude of the change. This may look familiar. This is the Pythagorean theorem, but in 3 dimensions. In Einstein's theory of special relativity, space and time are put on an equal footing in what is known as space-time. The motion of a particle can be represented by 4 numbers here, 3 for space, 1 for time. Time being scaled by the speed of light, putting the product in the same units as space. The magnitude of the 4 vector is then the Pythagorean theorem in 4 dimensions, with one caveat: time has a negative contribution to the vector's magnitude. This is the Minkowski Metric, or Minkowski Space, which is distinct from Euclidean space due to this negative sign on time. The magnitude of the vector is a Lorentz invariant quantity, meaning it is the same in all frames of reference. It can be expressed in terms of another time variable. These two times are the coordinate time and proper time of a particle. Coordinate time is the time an outside observer measures, and the proper time is the time experienced by the particle. These are the two times you see in time dilation and the twin paradox. We want to show that a universe with an average positive spatial expansion rate must have a beginning. What we observe is an expanding universe, not only expanding, but accelerating in its expansion. So, the average growth rate appears to be positive. To show that this implies a beginning to the universe, we'll start with the Friedmann Metric. The Friedmann Metric is a generalization of the Minkowski Metric with a scale factor A on the spatial terms. The scale factor is dependent on time and characterizes the expansion of space over time. The T in parentheses tells us A is dependent on time. To avoid hand cramping, physicists often set light speed, c, equal to 1. This scales all subluminal speeds between 0 and 1. The Friedmann metric then looks like this. You can also think of c as being absorbed and hidden in the time terms. We can do some arithmetic to rearrange the Friedmann metric equation to see how expanding space relates to the momentum of a particle. Divide both sides of the equal sign by the change in proper time. These terms look like speeds, change in distance over change in time. Multiply both sides by mass squared. Recall momentum is mass times speed. This gives us the energy-momentum relation in expanding space. E is energy and P is momentum. You can think of energy here to be like a component of momentum in the time direction. The energy-momentum relation may look somewhat familiar. If we put the c's back in and consider a stationary particle with 0 momentum, we get Einstein's famous E equals mc squared. If mass and energy of a particle are constant, and the scale factor changes with time, this demands that momentum also change with time. So we write a t in parentheses next to the p in the energy-momentum relation. With mass remaining constant over time, this means the relation applies at another time, t prime. And with the energy remaining constant over time, This means the product of the scale factor and momentum is also constant over time. This relationship will come in handy later. Galaxies are all moving away from each other due to the expansion of space. The way galaxies are moving away follows a trend. The speed at which galaxies are moving away from us is proportional to the distance from us. The ratio between speed and distance, the slope of this linear trend, is the Hubble constant, h. The Hubble constant is a measurable quantity of spatial expansion. It is called a constant because it is thought to be uniform over all of space. However, it is not thought to be constant over time. So the average we will be concerned with is the average Hubble constant over time. In particular, we want to compute the average Hubble constant over the lifetime of a particle, finite or not. H bar is the average Hubble constant. Delta tau is the lifetime of a particle. The lifetime of a particle, by definition, is the difference between the final and initial time. To the right of the equal sign is an integral of a changing Hubble constant over proper time from the initial time to the final time. This equation will allow us to place an upper bound on the lifetime of a particle. Keep in mind the initial time could be minus infinity, making delta tau infinite. The ratio between distance and speed of galaxies is equivalent to the ratio between the scale factor and the rate of change in the scale factor. The integrand from above can therefore be expressed in terms of the scale factor a. A little rearranging gets us an integrand containing the ratio of the two times, proper and coordinate time. In relativity, this is the Lorentz factor. Energy and mass are related by this Lorentz factor. That means we can write the Lorentz factor in terms of mass and energy. And from the energy-momentum relation, we can write the Lorentz factor in terms of mass and momentum. Recall the handy relationship we uncovered earlier. This gives us the Lorentz factor in terms of mass and momentum in an expanding universe. We can now evaluate the form of the average Hubble constant over time. The integrand we evaluated earlier in terms of the scale factor and Lorentz factor can now be expressed in terms of momentum and mass. To make reading this easier, I will ditch the t in parentheses convention. Instead, the time dependence is implied in a and p. The integral is now over the scale factor a rather than time. The limits on this integral are the scale factors at the initial and final times of the particle's life. The integral evaluates to this monstrosity. Let's just call this f, a function of the scale factor. This f function is positive and monotonically increasing with respect to the scale factor a. We can see this by plotting or taking the limits of the function. It can also be shown that there are no asymptotes. This means that for a finite value of the scale factor a, there is a finite value of f. All of this implies an inequality. F at the final time is greater than F at the initial time. This inequality further implies that the product of the average Hubble constant and particle lifetime is bound to be less than the final value of F. Rearranging this expression gives us an upper bound on the lifetime of a particle. Therefore, the lifetime is finite. This applies to any proper time span for all particles in the universe. The time experienced by each particle must be finite. This implies that the universe cannot be past eternal as long as the average Hubble constant is positive. Since we observe a positive and increasing Hubble constant, this suggests a positive average expansion, which would then imply the universe must have a beginning. There may still be room left for an eternal past if you consider cyclic or quantum cosmology models, where the particles we know of still have a beginning, but after another set of particles' histories come to an end. Thanks for watching. I hope this video helped you understand the Borde-Guth-Vilenkin theorem. Bye guys.